The ultimate combination of exponential, trigonometric, logarithmic, and rational function. We have the exponential function e of minus t, e to the power minus t, trigonometric function sine of t, logarithmic function ln of t, and rational function 1 by t. And how do we integrate this one? Okay, so there's a way we can like combine both of them in a single term. So that is, if we make a definition that this function over here, it is I of x, and then if we just differentiate the function with respect to x, then we just have partial derivative inside integral, yeah, and that gives us t to the power x minus 1 times ln of t dt. Now if we substitute x as 0, now, and we get the required integral, isn't it? Integral from 0 to infinity e to the power minus t sine of t, and then this is 1 by t ln t. So our aim will be to solve this integral and then differentiate and substitute 0. Yeah, now let's do that. Integral from 0 to infinity of e to the power minus t sine of t to the power x minus 1 dt. Yeah. And now, like, how do we? Okay, so let's write this variable as m, like, because m sounds more nicer as a constant than x sounds. Okay, I of m. Now, how do we solve this one? Basically, just our guess can be to use series expansion for sine of t and then see if it is helpful or not. We aren't really sure though if it will be helpful, but yeah, we can try that. Integral from 0 to infinity e to the power minus t to the power m minus 1. So I'm going from n equals to 0 to infinity, minus 1 to the power m t to the power 2n plus 1 by 2n plus 1 factorial. Yeah, and then we have dt. Now let's take the constants inside, interchange sum and integral. Sum from n equals to 0 to infinity, minus 1 to the power n by 2n plus 1 factorial. Integral from 0 to infinity of e to the power minus t to the power m minus 1 to the power 2n plus 1 dt. Now this is I of m. Yeah, now if we try to differentiate this function, what do we get? Why to differentiate? That we haven't really solved this integral. First of all, let's solve this integral and then we will talk about that. Minus 1 to the power n by 2n plus 1 factorial. Now its integral will be, we basically have t to the power 2n plus m. Yeah, so that's why we will have gamma 2n plus m plus 1, and yeah, we will have this expression. Now this is I of m. Yeah, and now if we have to find I dash of 0. Yeah, so I dash of m will now be sum from n equals to 0 to infinity, minus 1 to the power n. This is gamma of 2n plus 2, and this is gamma dash of 2n plus m plus 1, and then okay, yeah, that will be. And now we know that gamma dash is just gamma times digamma, so that's why we can have I dash of m as sum going from n equals to 0 to infinity, minus 1 to the power n by gamma of 2n plus 2. Yeah, and then this is gamma of 2n plus m plus 1 times digamma of 2n plus m plus 1. Yeah, now if substitute m as 0, what do we get? I dash of 0, because that's what we want. Yeah, sum from n equals to 0 to infinity, minus 1 to the power n this is gamma 2n plus 2, and then this is gamma 2n plus 1. So we have 2n plus 1 remaining over here if we cancel out them out, and this is digamma of 2n plus 1. Okay, so we got this infinite sum, and that is our answer. But it doesn't really look nice. Like, can we try to make it better? Because the original answer, like that I found in Wolfram Alpha, is somehow nicer. Though it's in terms of pi, but we see that over here? Okay. So to simplify this expression, what we can do is we can use the formula for digamma function of 1 plus x. We know that this is negative of Hermastonic constant plus h of n. Yeah, we will use this, and that gives us sum from n equals to 0 to infinity minus 1 to the power n by 2n plus 1 minus Hermastonic constant, and then plus h of 2n. Yeah, here's in terms of x there is 2n. So now this is sum from n equals to 0 to infinity minus 1 to the power n minus of Hermastonic constant by 2n plus 1. Yeah, plus sum from n equals to 0 to infinity minus 1 to the power n, and then h of 2n by 2n plus 1. Yeah. Now over this one, like you might probably remember this sum. Yeah, because we know that the series for tan inverse x is sum from n equals to 0 to infinity minus 1 to the power n x to the power 2n plus 1 by 2n plus 1. That's why this sum is just tan inverse 1. Yeah, and that's pi by 4. So this over here is just negative Hermastonic constant times pi by 4. Now let's see how what these will evaluate to the other expression. Sum from n equals to 0 to infinity minus 1 to the power n by h 2n by 2n plus 1. Okay, we will begin with the generating function of skew harmonic number with base 2n. Yeah. And then we will try to get, okay, so what do we begin with is sum from n equals to 0 to infinity minus 1 to the power n h 2n x to the power 2n. We will begin with this because generally it's easier to find generating function, and then we can integrate it to get this expression. So to find this, we will just use now this the integral representation of h 2n. Sum from n equals to 0 to infinity minus 1 to the power n integral from 0 to 1 minus t to the power 2n by 1 minus t dt x to the power 2n. Yeah, and then integral from 0 to 1 sum from n equals to 0 to infinity, we have minus 1 to the power n 1 by 1 minus t, and over here we have x to the power 2n minus xt to the power 2n. Yeah, and then dt. Now we can use the geometric series representation for these things. Integral from 0 to 1 by 1 minus t. Now here the first term is x square and the ratio is minus x square. So for first term is 1 and the ratio is minus x square. So that gives us 1 by 1 plus x square minus, this gives us 1 by 1 plus x square t square. Yeah, x square t square dt. Now let's just first take the LCM, and then let us see what we can do next. 1 by 1 minus t, we get 1 plus x square t square minus 1 minus x square by 1 plus x okay, wait a second. Seems like it's going fine. Yeah, seems like it's going fine. But wait. Okay, let's see where do we reach. Yeah. And 1 plus x square 1 plus x square t square, and then dt. Now what do we have? Integral from 0 to 1. If we take this 1 cancels out. If we take x square common, that's a minus x square common, we have 1 minus t square. Yeah, over here that's 1 minus t, 1 plus x square, 1 plus x square t square dt. Yeah, now we can take minus x square, and note that we also have to integrate the result that we we will get. That's an awesome thing. Integral from 0 to 1, 1 plus t by 1 plus x square dt. Now this one is easier to integrate. We can integrate part by part. Yeah, minus x square by 1 plus x square. In the first part will be tan inverse xt by x. The second part will be, we can take 1 by 2, there's 2t, and then ln of 1 plus x square t square by x square. Yeah, okay, fine. And then that's nice. Okay, and so this is from 0 to 1. What do we get next? Minus x square by 1 plus x square. This is tan inverse x by x plus 1 by 2 ln of 1 plus x square by x square at 0, both are 0. Okay, now let us multiply by x square and also take 1 by 2 common. We get minus 1 by 2, and then this is 2x by 1 plus x square tan inverse x plus or minus plus, and then this is multiplied x square. So ln of 1 plus x square by 1 plus x square. Yeah, this is the thing. Yeah, now we have to again this is just, we know that what is this. This is sum from n equals to 0 to infinity minus 1 to the power n as to n x to the power 2n. Yeah, but the result that we want is not is this, but we have to have 2n plus 1 denominator, so we have to integrate this expression. Yeah, now let's integrate both the expressions, and notice that this thing over here isn't product rule. Basically, if this is u, if this is v, its derivative is just dv is here. Yeah, 1 by 1 plus x square and then 2x, its derivative is here du. So this is in product rule, that is in duv. That's why the integral is easier, minus 1 by 2, and then u is tan inverse x. Yeah, and the v is ln of 1 plus x square. Yeah, let's integrate from 0 to t, let's say from 0 to t, and that this is from 0 to t. Over here we get sum from n equals to 0 to infinity of minus 1 to the power n as 2n x to the power 2n plus 1 by 2n plus 1. Yeah, and so over here we get just minus 1 by 2 tan inverse x ln of 1 plus x square at 0. This is 0, and so this is the expression. But again, this is also not the thing that we want. What we want is the case when x equals to 1. If we substitute x as 1, what do we get? This thing over here will be the required expression, that is sum from n equals to 0 to infinity minus 1 to the power n as 2n by 2n plus 1, and this thing over here will be minus 1 by 2, tan inverse 1 is pi by 4, this is ln of 2. That means this is minus pi by 8 ln 2. And this is a well-known number. It comes in a lot of places, minus pi by 8 ln 2. So we finally have the result of our all of this work. Yeah, this one. And now we know that the other thing expression is minus. Sorry, let me zoom in first. Okay. So this is minus Euler Masonic constant pi by 4 minus pi by 8 ln 2. And let me see if we can if this is correct or not. Okay, so basically let me just take pi by 4 common out, and also the minus sign common out, minus pi by 4. That gives me gamma plus ln 2 by 2, and that's the correct answer. This is the answer that's there, ln 2 by 2 minus pi by 4 where Masonic constant plus ln 2 by 2. Yeah, and this one is finally minus pi by 4 where Masonic constant plus ln 2 by 2. And it feels so nice to have integrated such combination of a lot of different functions. And yeah, so to talk about the flow of the solution, okay, this is too long though. We talk about the flow of the solution. We first found a way to make the integral simpler using this expression t to the power x minus 1, and use the series expansion of sine function, interest sum and integral. Here we used gamma function, and then we differentiated, substituted x equals to 0. We had the answer over here, but okay, so if this was the answer, it was too short, yeah. But then this was not the answer, and basically this expression was way longer than the original solution, yeah. And then we expressed tie gamma in terms of constant in h to n, and this was also a well-known sum. And for this one, we went through a lot of verses. We used this integral expression, interchanged, and then found the answer finally. And then again, this was this was a coincidence or something like that, or maybe there's a different way to evaluate this, which makes it easier. But and I'm not really sure. Maybe the solution of this original expression is a different one, which gives this answer easily. But here, it was kind of coincident that we have this product rule, and we used product rule to integrate this, and finally we got the answer for this sum. And putting that sum answers, we got the original result. And the answer is beautiful, minus pi by 2 Euler Masonic constant plus ln 2 by 2. Hope you enjoyed the video. Thanks for watching. Look forward to seeing the upcoming videos too.